So we've just done Gaussian elimination, and so far we've seen what happens when everything goes right. Thinking of a system of two equations in two variables, that's easy to understand as they're just lines in the plane. And the typical situation is our lines in the plane just cross at one point. Completely different lines, different slopes, they cross. It's also possible that there's no solutions, in which case if the lines are parallel, then they don't cross at all. And if the lines are actually the same line, of course they could be in disguise because one equation might be, say, twice the other equation, but if they come out to be the same line, then there are infinitely many solutions. With Gaussian elimination, you can see those cases as well when you try and reduce to the lower triangular form. So let's just look at a few things that can go wrong. Well, first of all, our recipe for solving it is meant to be a recipe that you kind of follow blindly, so you can program it on a computer. Because of course, if you're just doing it by hand, you kind of look for convenient arithmetic and might swap things around a bit more. But if you wrote down the equations and the first equation doesn't have an x1 in it, then you're stuck for doing Gaussian elimination. So all you do is you swap that with the next row. So you swap row 1 and row 2. And actually then you've already got a 0 in this position, so the next thing you do is get rid of that number. I mean, you could say if you're doing it by hand, you'd probably swap the row with the 1 up to the top just to save your effort. But programming that sort of thing turns out not to be necessarily as efficient. You've got to kind of think of all the possible cases. But in this case, we just swap until we've got a non-zero in that row, and then we carry on with Gaussian elimination. And as long as that always works, I mean, as long as each time you can swap something up that's non-zero, then you carry on with a Gaussian elimination. I suppose the worst case is that if you keep getting zeros, then eventually you just get a row of zeros, in which case things are obviously going to go wrong because one of the equations has disappeared. We've got too few equations. So, in a way at that point, you know that the matrix was actually singular. So suppose we've done that and we'd ended up with our lower triangular matrix, but it's got this extra 0, and in other words, there's a whole row of zeros. And let's suppose that it's turned out that the right-hand side number there is 0 as well. Well, there isn't going to be a unique solution because we've got two equations in 3 variables. And the last equation means we can't find x3. So what we do is you just give it a name and we say it could be anything. So we've got x3 equals lambda. And then back substituting, we've got 2x2 plus 3 lambda equals 6, from which you can rearrange to get x2 in terms of lambda. And then putting it back in the first row, we get x1 in terms of lambda. And it turns out that x1 is just lambda over 2. So we have infinitely many solutions now, one for each choice of the real number lambda. We can write it in this way, x1, x2, x3, and here's the expressions we've found for those in terms of lambda. If you pull out all the things with lambda in and leave all the things without lambda, you can see it has a particular form that it's a vector 0, 3, 0 plus some multiple of this vector. So actually, this is a vector that gives you the desired right-hand side that you want, and this is it's kind of any vector that when you apply the matrix you get 0. So it kind of doesn't affect the right hand side. So there's a kind of neat interpretation of that. You can call it the unknown anything you like, and of course if you have a bigger system and you get more rows coming to 0, then you have more variables you can't find and you have to call them different, typically Greek letters, lambda, mu, and so on. Well, something can go even worse than that. Suppose we get a row of zeros for the x variables, but we get a 1 on the right hand side. So this says 0x1 plus 0x2 plus 0x3 equals 1, which can't happen. It says 0 equals 1. That means there are no solutions, and our equations were inconsistent. Of course, there's a geometric interpretation of this as well. Each equation is a plane. If we had two of the planes were parallel, then they wouldn't cross and be no solutions.